All right, so I'm going to take over the screen here. So hi again, everyone. I don't think I met everyone in the HydroLearn group, so it's nice to see some other people that I didn't get to meet. So we decided to do more of a PowerPoint presentation, but of course, informal, so feel free to stop me and ask questions. And so this module, as Melissa mentioned, was created by myself. I'm a professor at Wake Forest University, Zudi Aljiba, who is a professor and a professional engineer at Valparaiso University, and Damien DiVittorio, who is a professional engineer at Columbia Engineering. And so when we thought about this module, we first thought about the students that we were creating this for. So our students would be enrolled in an introductory hydrologic engineering course. In our heads, they had already learned some fundamentals of rainfall runoff processes, and this would be an application of those fundamentals. And so the students want some experience in applying these fundamental concepts while solving an authentic real-world problem and using an industry standard software. And so we're using a tool called PCSWMM. It is a commercial software, but if you are associated with the university, you can get an educational license for your students. And this is the most commonly used software to do kind of stormwater and hydrologic analysis in industry, at least according to a lot of the professional engineers and the two involved in our research in this module development. So similar to the last module, we really wanted to motivate students with a problem. And so this focused on a case study and a specific problem that needed to be evaluated. And so I've been working with the facilities at Wake Forest University to get some data and some historical imagery of the campus. So we kind of show them and give them background on how the campus has changed over the years as it's developed, and highlight some of the erosion issues they've had on the campus and how they've had to invest money in doing some retrofit. And so there's room for improvement in terms of improving the way that stormwater is managed on campus. And then they have this little interactive map, which was Maud's recommendation, where they can kind of look in on Google Earth or Google Maps and view the campus and some of the photos that we showed them earlier. And so then they're told, they're a design engineer working for a firm, and they need to characterize the watershed under the pre and post development conditions, so before the campus was developed, and then perform a pre and post development hydrologic runoff analysis using the software, and then implement a stormwater improvement by designing stormwater quality and quantity controls to reduce the runoff. And so we use these kind of three tasks to outline our module in 3 sections. And so Damien's going to start with the first section.
So in section 1, the learning objectives that I wanted the students to get from this were to be able to delineate using a topographic map and a point of interest, and then also understand where they can get soils information and understanding how hydrologic soil groups are used in hydrologic models. And then also wanted the students to understand land cover classifications and how that information is used to inform hydrologic models. And then also be able to use the GIS tools, which are commonplace in practice, to create data sets that can be used as input to models. So our first learning activity is actually the delineation of a watershed. So this is a sort of a sample watershed that is used throughout the videos that were produced for the course or for the module. And so I sort of take them through the process of how I delineated this, and then asked them to delineate to a point on campus. And they're given contour data, they're given campus stormwater network data, and told to also use desktop analysis to inform their delineation. And then learning activity 1.2 is creating the pre-developed CN number, which is runoff curve number, and percent impervious. So students are given a aerial image from the campus in its pre-developed state, and it's been georeferenced, and they can have that inside the software. And then they're also given the TR55 curve number tables and asked to use the tools inside the software to break up the delineation into different land cover classes with CN numbers, and using the hydrologic soil group to get the CN number, and also characterize the percent impervious for each of those different sections, as they will be used as input for their pre-developed scenario. To help the students have the information that they need to do these learning activities, we take them through an introduction to PCSWMM, where we talk about different types of GIS data. So just briefly talk about vector data, raster data, and how they're used. We also, the company that develops PCSWMM has some great learning activities and hands-on exercises. And so they're asked to go through the creating your first model exercise, and then we provide some check your understandings. Next slide. And then the for watershed delineation, we've got video instruction that takes them through sort of the process of delineating a watershed using contours and other information. And then, oh, go back one. Develop some check your understandings for ensuring that they can read a contour map and get some elevations off a contour, and sort of try and visualize what the contours are telling them. Next. Okay, and then talk about hydrologic soil groups, why soil information is important. Talk to them about the different hydrologic soil groups, and actually embedded as an iframe in the module, the soils report for the sort of sample watershed that I'm taking them through in the video lectures. And then for, we have a discussion of different infiltration methods used in the SWIM engine. For simplicity and sort of ease of use, we're using the CN method, but mentioned some of the other ones that are available in the SWIM computational engine, and take them through how to create those data sets using the GIS tools inside of PCSWMM that sets them up for learning activity 1.2.
All right, so that brings us to section 2. So again, we started with the learning objectives. And so in this section, we want students to be able to understand the SWIM hydrologic model that they're using, download and interpret design, storm, rainfall data from NOAA, and use the model to produce the hydrographs and quantify differences between them for pre and post development conditions, and then relate these watershed characteristics to the runoff hydrographs and perform a parameter sensitivity analysis. So then the learning activity was aligned with these objectives, since you know, had a lot of practice with the constructive alignment. Thank you, Melissa, for keeping us on track. So these tasks align really well, and to give them the content to complete that learning activity, we first started with some background on the SWIM hydrologic model within the software. And so there's actually another group that had a module focused on PCSWMM, and so we kind of collaborated here. So some of the equations and figures were borrowed from David Spellman and Gianna Catherine, who are presenting next week, and kind of adjusted for our module. We also point them to an instructional video that kind of walks them through the different equations. And then, of course, there's check your understanding. So before they implement the model, we want them to have some kind of conceptual understanding of how it works. And then they need to identify parameters in their model. So we go through a few of the different model parameters and give them images to try to conceptualize what they mean and how they're represented in this model. And then that's also has some instructional videos of how to set the parameters within the software. And again, there's some check your understanding questions. And then they finally learn how to bring it all together and implement the model. So they have to use the watershed characterization data that they had to produce in section 1, and also bring in other information. So they get the design storm data, and upload it into the software. They have to, set up their outfall point where they're doing their hydrograph analysis. And that leads them to the learning activity where we give them the results template. So they can, as they're going, they can add in the results. And then we have some summary questions. So I just have an example here is where they discuss the results of their hydrographs in the context of their watershed characteristics that they explored in section 1. And then which watershed characteristics help explain the hydrographs and give some examples and relate them to physical relationships. So these questions are meant to, make connections between the various sections and make sure they understand that how they're using the data they're producing, how it's used in the model, and how it affects their results. So that brings us to section 3, and I'm going to stop sharing so Zui can take over.
Okay, good. By the time the students get to section number 3 in here, they should have the hydrographs for the pre and post. If they successfully completed those 2 sections, sections 1 and section 2. And you see in section 3 in here, this is the time for them to more or less figure out the sizes. We do not go in details in the design process, but the sizes of the detention pond to be specific needed for the watershed, and then what type of LIDs they will be implementing to both for the quality treatment of the stormwater shed. So in this section, divided this into 3 subsections and a learning activity, 3.1 in here. So I'm gonna go over each of those sections. So starting with the introduction to section 3 in there, it simply gives them a summary of brief description of what will be accomplished within this section. As you see in here, this is a screenshot from the HydroLearn module, and then we go over the learning objectives. Now I could go back to the learning objectives, but I tried to actually more or less use the Bloom's taxonomy in here and going between level 1, level 2, 3, and 4, all the way to 5 in terms of remembering, which is list and describe, understanding, analysis and apply, all the way to the create and analyze in there. And then I move into the background, give them a little bit of brief description about the different green infrastructures, low impact developments, best management practices that are usually used in practice. As Courtney mentioned there, I've been practicing as a stormwater engineer, civil engineer in general for so many years, and that's what we actually do in the field. So this is very authentic in that sense. Share with them a video from the EPA about actually the different GIs, LIDs, PMPs in there. So they get a good sense, good feeling about the different green infrastructures, low impact developments, and so on. Then I go into the second subsection, which is focused on green infrastructure used for flood control. And you will see in the next section where I will focus on the quality control. Divide that again into like some background, give them a brief description of the common flood control measures, focused in this case on retention, detention, wet bomb basins, as you see in this naturalized detention pond. Actually, it was a dry bomb, concrete bomb. It was converted. This is in my neighborhood in here in Valparaiso. And then go and talk about the other different types of flood controls from the wet or dry bomb detention ponds, show them an image, constructed wetlands, retention ponds or wet ponds. That's again describes a little bit about the type of soil that you need to be selecting between those different ones. And the underground detention facilities are currently being used in urban settings where you don't have enough space to actually put a detention pond or something like that in there. So for each one of those, goes in one section. They have images with references to those images in there. Then the next section was to give them a hands-on exercise, going back to what Damon just mentioned, that PCSWM comes with a very good library with like actually hands-on exercises where they could download the exercise and the files and go through it. So we require that they go through 2 of these in section 3, one for sizing, as it says in here, design of an inline stormwater pond to meet pre-development conditions. The next one later comes, which is how to implement LIDs in the design process. So that takes me to the LIDs, as you see over here and there. Give them a little bit of background, describe a few of those LIDs being used, then go over the parameterization, and then a hands-on exercise. Okay. Am I running out of time, Melissa, or not yet?
No, we have about 5 minutes left total.
Okay,
So
good. So this is the background where actually give them a video clip where LIDs, BMPs, and IG is being implemented in an Indianapolis area, public area, actually in there. It's a very nice like video clip where they get to see them in reality, give like some background and then some like links to design manuals and the EPA website where they have like a more detailed descriptions of those like LIDs in there. So if somebody wanna design those LIDs, there are like the links to like design manuals in here. I focus on, I believe 3 of them in here, green roofs, show that in here, rain gardens, and buffer areas. And so give them descriptions, pictures to see before we move into PCSWM, how to implement all of these LIDs into PCSWM. And so talk about the main components, give them an image from the EPA SWM model, which is PCSWM took, but they changed the image a little bit in here, the main components, and then we talk about the different parameters they have to do. Along the way, there is a check your understanding about what LIDs are implemented in PCSWM, and then take them into those like what we call the LID control editor in PCSWM, and the different parameters they have to be inputting, and actually give them, before I do that, ask them to go through a hands-on tutorial exercise that comes with PCSWM, then go through the description of those different parameters in the model. Finally, we get to the actual work, which is, in my case, I've been doing this for so many years as a semester project, which is simply come down. They go through like section 1 and section 2, starting with a contour map, delineation, creating the hydrographs, and then end up with the implementation, finding out the size of a detention pond, and the implementing LIDs. Now, from year to year, I change the requirement. There are some years I say we do not need a detention pond, but you have to implement enough of those LIDs to have 0 excess runoff. And so it's up to the instructor how they want to go about it. They may ask them to implement so many of those LIDs, and then ultimately come up with the size of a smaller detention pond if there is just not enough room to implement some of those. And then, as usual in that, it's an authentic problem. We require that they create a report, actually. We tell them exactly what results we are looking for in here. So there are 10 of those to be included in the report. Give them some sources of information, including those hands-on exercises, instructions how to actually access the exercises and to go through them. And then finally, there is that rubric for the grading their report comes at the very end. That's the end of our presentation. I will stop sharing and go back to the main room in here. And if you have questions, you are welcome to ask.
Yeah, we have about a minute left. So if there's anyone with, let's take one question for this group.
I do not see anything in the chat box.
So was the watershed delineation, was that done by hand drawing on the contours?
Yes, yes, it was. And I forgot to mention, actually, it kind of goes back to the first group that presented. Why are we doing this? Don't we have computers to do it? And I actually asked them to go to stream stats and delineate. And I come up with a slightly different watershed when I do it than stream stats. And so I asked them to talk about the difference in the learning activity, because stream stats, I don't feel it doesn't take into account the small infrastructure in the ground. And so having that as a base layer that they can use for the delineation to inform their delineation will show them the differences.